Hello, everyone. My name is Laura Villalobos, and I'm the WISIS Community Manager. I would like to welcome you to this WISIS webinar with Sandia's National Laboratories on the topic of toward real-time instruction selection in cyber networks. But before we start, I'd like to introduce you a little bit about the WISIS organization. We often go by our acronym WESIS, as in We Sisters, because that's exactly what we are, a global cyber sisterhood. We are a 501c3 with over 7,000 members in 70 countries. WESIS is a premier organization with a global reach dedicated to bring together women in cyber. Our mission is to recruit, retain, and advance women in cybersecurity. All of our programs and initiatives are made possible by our supporting strategic partners such as Sandia. We have our professional affiliates, student chapters, volunteer committees, mentor-mentee program, chat board plus members, and so much more. You can view our training programs and initiatives on our website at wesis.org to learn more about the different ways to get involved within the WESIS community. We owe everything to our strategic partners, our tier one partners being Alchemine, Amazon, Battelle, Boomerang, Cornell Mellon University Software Engineer Institute, Cisco, Fortinet, Google, Lockheed Martin, Meta, Microsoft, Optum, Sandia National Laboratories, and Sentinel One. Reminder to ask questions throughout the webinar so you can put them in the chat and the presenter will ask them at the end. We have the experts here with us today and they look forward to hearing from you in the audience. If you haven't done so already, be sure to subscribe to the WESIS newsletter at wesis.org to stay up to date on any upcoming WESI events and trainings. With us today, we have Sandia National Laboratories, and we'll have them kick it off.
Thank you. Hi, I'm Leka. I'm a computational statistician at Sandia National Labs. I'm going to give a review presentation about intrusion detection in cyber networks, which will focus on current methods and analysis of features that we typically see in cyber networks before discussing some of the challenges for real-time detection and some of the problems we're actually tackling currently at Sandia. I am a statistician, so I don't really have much experience in cybersecurity, and I've just kind of got into it. So I'm really excited to be giving this talk. This is joint work with Doug McGeehan, Erin Schwetner Watson, Gabriel Huerta, Professor Fletcher Christensen at the University of New Mexico, and Mayuri Shakamori, all at Sandia. So just to give a brief overview, in this talk, I'm going to give an overview of intrusion detection, specifically what cyber intrusions are, what types of cyber intrusions exist, then kind of moving on to intrusion detection systems or IDSs, and the two typical types, so signature-based and anomaly-based. Really going to focus on anomaly-based in this talk, given my kind of statistical background. So we'll go into traditional approaches and recent for the previous 5 to 15 years, this huge kind of flux of machine learning approaches for IDSs. Then we're going to go into data sets, so specifically what features of cyber data can we use for IDSs. I'll talk about public IDS data sets, really focusing in on exemplar data set, which is the NSL KDD, which has been widely used in the literature. Some of the challenges, feature selection, computational costs, and then all kind of related to this NSL KDD dataset that we've been looking at, Sandia. And then going to give kind of a brief overview of what we need to be doing for real-time intrusion detection systems to be more robust, and some of the work done at Sandia before going into references. So what is intrusion detection? For those of you who are unfamiliar, there are a range of different cyber intrusions. So this is denial of service, which attacks these attacks attempt to interrupt normal traffic or the network by overwhelming the target network or server with a flood of network packets, which really prevents regular network from reaching its actual destination. This is the most kind of common type of attack. Then we have remote to local. These are attacks where a remote machine sends packets to a local victim machine, which are then able to learn the user's activities and then gain local privileges on that machine. There's then user to root, and here the cyber criminal will access a normal user's privileges at the beginning, and then use that to upgrade to become a super user, which can lead to exploitation of the system and specific vulnerabilities of that system. There are then probing attacks, and these attacks, information is acquired about the network, or computer system, by scanning the network to gather host data packets from valid kind of IP addresses. So, what are some of the intrusion detection systems that exist? So, intrusion detection systems are systems to actually be able to detect these kind of intrusions that we do see in cyber. So, these kind of four different types of intrusions. There are actually a lot more. The first or classical kind are signature based intrusion detection systems, which use signatures. These are typical kind of footprints or patterns that are associated with a kind of intrusion or a malicious intrusion or attack on a specific computer network. Some examples of signature based IDSs include looking at things like network byte streams or sequences. These are a series of bytes, or malicious intrusion sequences. Signatures can also come across through unauthorized software execution, directory or network access, or anomalies in the network privileges. And typically, signature-based IDSs have been around for a while, just to look at these type of patterns, byte streams that exist for particular types of intrusions or malicious activity. And they're useful in detecting known attacks. So these are things you'll find on your anti-software, but are unable to identify new threats that potentially would have new kind of signatures. So what's the other type? The other type is anomaly-based IDSs. And these have been used to detect unknown types of signatures and attacks. The way this is done is through kind of statistical machine learning, deep learning methods. And the way they do this is by probabilistically quantifying a baseline kind of statistical distribution of benign or normal network behavior, um, and flag intrusions or events that are anomalous if their kind of patterns show deviations from the specific baseline distribution that the statistical machine learning algorithm has been able to quantify for benign behavior. So, in contrast to signature-based intrusion detection systems, they are useful for detecting zero-day attacks because they don't need to have known a particular signature of a particular type of attack to detect it. So, particular methods include machine deep learning methods or statistical time series analysis or knowledge based methods. And here's kind of example here of a statistical kind of time series based analysis. So in the blue is benign activity. In the red shows kind of intrusive activity. And what the statistical algorithm will do is it will be able to quantify the distribution of these benign or normal events in the space that they're in, and then essentially find or quantify some sort of threshold to then classify events that kind of lie outside of this distribution in some way as an intrusion. So, what are the traditional methods for anomaly based IDSs or intrusion detection systems? A lot of these traditional methods come from the signature based IDSs. Examples include Snort and NetStat, for those of you who are familiar. And these are, of course, feasible in real time, and they're fast for known signatures. This is why your antivirus software works really fast. But it is unable to identify new malicious attacks for those that have kind of new signatures associated with them. The second type of traditional method are the statistical methods. An example here that I just showed was time series anomaly detection. This can be potentially slow given the amount of cyber data that it's using. And the way this works is flagging new observations as abnormal or an intrusion if the probability of its occurrence is too low relative to this normal distribution or this benign distribution that the algorithm has quantified. Some kind of issues here is that it can have low accuracy or high false alarms if the number of data it's been using is kind of low. The next type is knowledge based, and this is a really interesting type of intrusion, or sorry, an algorithm. Sorry, and examples here include kind of signature analysis, expert systems, finite state models. For those of you who are familiar, so knowledge based algorithms are really cool because they have a human in the loop. And what the human in the loop does is it allows the system to create a sort of knowledge base that reflects legitimate traffic profiles, and then actions or events that it sees that differ from this knowledge base that the human has helped create are treated as intrusions. And this is really nice because you are using human knowledge. We have a human in the loop. We can reduce some of the false positives that typically occur in some of the traditional statistical methods. But one of the drawbacks here is that regular updates are needed when we're looking at new data. Of course, with a human in the loop, feasibility in real time is difficult. So I'm now going to move on to machine learning methods. So these type of methods have really come up in the past 5 to 15 years in terms of anomaly-based intrusion detection systems. Machine learning methods are classified into kind of three different parts. So we have unsupervised machine learning methods, semi-supervised machine learning methods, and supervised machine learning methods. These three different methods are based upon the actual data, or training data they call it, it's used to be able to inform or train the algorithm with known or unknown labels. And a label here is a specific intrusion or type of intrusion that is associated with each kind of event or data stream. So starting with the unsupervised methods, so this kind of draws back from a lot of the previous statistical analysis that has been done in the area. Unsupervised methods do not require training data, so we don't need a label for each of the data points, which labels an event as an intrusion or not, or type of intrusion. And typically, these methods are clustering methods. An example here is the k-means algorithm. And the way they do this is very similar to statistical based algorithms, which kind of probabilistically define normal benign behavior through clusters generated by the algorithm that use distance measures between events. So, for example, if an intrusive event is really far away from a benign event, that would indicate that they belong to different clusters. And so different clusters for intrusions and benigns will be created with this unsupervised approaches. But classification of specific intrusions, such as kind of user to root, DDoS attacks, these kind of things, are going to be difficult without kind of known data leading to specific distances that create barriers between these clusters. Of course, unsupervised methods are usually feasible in real time given the computational efficiency associated with them. We then move on to semi-supervised. So these algorithms use a small amount of labeled training data. So this labeled data has labels associated with each kind of data point, labeling as attack or no attack. But doesn't need to cover all intrusion patterns. So this is why it's semi-supervised. So we have a kind of supervised part and a non-supervised part. Examples here include graph-based methods or fuzzy-based neural network outputs. And the fuzzy-based algorithms here are typically used to define not just a class associated with each event. So it's not just an attack or no attack, but actually gives some kind of probability or weight associated with the classification of each event to a particular attack or not. So these methods are typically pretty slow in real time, especially with a huge amount of data. And this is because retraining is typically needed as we see new data points. So we have to retrain the semi-supervised algorithms, and this can be slow. And of course, with a lot of statistical machine learning based algorithms, high positive or false alarms can be brought on by these algorithms. We then move on to supervised algorithms. So there are a ton of algorithms in the literature, and I'm sure a lot of you are aware of these. So, for example, decision trees, neural network architectures, nearest neighbor approaches. And supervised methods are really, really fast to implement in real time if we have a trained model. So, a trained model is actually training one of these classifiers or algorithms with a training data set, which has known events with known labels. So, we know exactly what type of attack each event is associated with. Again, a drawback here is that it does require this labeled data for intrusions, and I'll get onto this in a minute for this training. But for a lot of important or at least interesting types of attacks, there aren't really public data sets that we can use to train a lot of these algorithms. So without training, we can't really get the efficiency associated with feasibility in real time from supervised algorithms. Again, depending on the number of training points, high false positive rates can occur. And this kind of is a huge drawback for a lot of these kind of algorithms on real cyber networks. So, what are some of the real time challenges with using a lot of these approaches? So, typically, intrusion detection systems monitor a flood of raw network data and system event data in real time. And it's really this real time that we're looking at in this presentation and we're working towards in kind of future algorithms that we're posing. So, given the data, and I will talk about a lot of the data in a minute, but some of the features that can actually be extracted from cyber data sets are immediately observable in real time, right? So this requires no additional processing. We already have the data and we can use it in any algorithm that we wish to pursue. Some features of interest for certain attacks um, require maintaining a log. So this requires recording certain information on what's happened up until that point. This puts a bit more pressure on our system, so we need to actually have certain data points from the history in memory to be able to put this into our algorithm. And then some features that are useful for detecting certain intrusions require generating new information or new features using knowledge of other data sources, for example, with data fusion, that are not directly observable from network data. And so this kind of picture really shows is exactly what real-time intrusion detection systems we're trying to build with greater accuracy. So we have real-time cyber network traffic. We want to do some kind of feature extraction to get features that best represent the intrusions that we're really trying to detect. And we're then going to put this into our intrusion detection system, whether that be statistical, machine learning, or something else, or knowledge base, or something else, which is then updated periodically as we get new data in real time. And then that feeds into kind of a detection decision theory or decision point, whether are we detecting an intrusion or not, which then alerts to the user. So those were some of the methods used for detecting intrusions. But what is it exactly about the data that is used to train or devise certain really good algorithms for real-time intrusion detection? So, a lot of the data sets that are used in the literature that use a lot of these machine learning or statistical techniques for anomaly based intrusion detection come from a lot of public IDS data sets, which are, public, anyone can download them. And there are quite a few of these IDS data sets that analyze network traffic. Kind of caveat here is though there are limited variety in the types and densities of attacks that certain kind of servers may be wanting to detect. And this is due to the rarity of high impact intrusions that occur in a lot of these data sets and do occur in real life. So the earliest effort to create an IDS dataset was actually by DARPA in 1998. This was collected by multiple computers that were connected to the internet to model a small kind of US Air Force base with restricted personnel. Here, network packets and host log files were collected as a series of TCP sessions with start and end times, containing a large variety of attacks that were simulated actually in a military network. So this original data set, which has been kind of the basis for a lot of this anomaly-based analysis in cyber networks, came from the DARPA data set. This had 41 features initially. The KDD CUP 99 dataset was then developed from the earlier DARPA dataset, just kind of improving it a little bit. The main problem that was realized in this data set was that it had a huge amount of duplicate packets. So approximately, I think it was at 78 to 80% of the training and test data were duplicated in the number of data points that they had. And so having duplicate data points really biases a lot of statistical and machine learning methods and really kind of brings up that high false alarm rate. And so, given this, the NSL KDD dataset in 2009 was built from this KDD 99 dataset to resolve a lot of these issues. And this kind of produced consistent and comparable results from various procedures. This had 22 different types of intrusions and 41 different features. The ADFA data, this is from the Australian Defence Force Academy on both Linux and Windows machines, was then built to represent structures and methodologies of actual modern day attacks. The attacks in the ADFA LD were derived from new kind of zero-day malware, making this really suitable for highlighting differences between signature-based and anomaly-based approaches. And then recently, and this is a data set that we're looking at Sandia, the Canadian Institute of Cybersecurity IDS data set, CIC IDS 2017, comprises of both benign behavior and intrusive behavior, and also details some really new malware attacks that haven't been previously introduced. These include brute force attacks from SSH or FTP, DOS, DDoS attacks, infiltration attacks, with 80 now network flow features. So some of the things that we've noticed here is as we get new public data sets, the kind of difficulties of actually finding or detecting intrusions gets more difficult, more challenging. The different types of intrusions increases, and the number of features actually in the data set increases too. So we initially what we did was we looked at the NSL KDD dataset. And this was characterized, and this is characterized, sorry, by three different types of feature sets. So we have basic features, um, aggregated traffic features, and connection content features. And this kind of aligns with the computational efficiency and computation needed, and the information represented by each of these different features. So with the basic connection features, this includes connection duration, the network protocol type, the connection status, flags, that kind of thing. And these can be, these features are just directly obtainable. Then we have aggregated traffic features. These are features that are computed within specific time windows. That includes details and the number of connections during the previous 2 seconds. Here, aggregated traffic features are grouped into two, so as containing the same host and the same network service features as the current host or connection. Specific feature examples here include the sum of connections to the same host as the current connection over the past 2 seconds. Over the past 100 connections, the sum of connections to the same host as the current connection. We then move on to connection content features, which aligns with what I had previously said. These are the most kind of difficult features to derive because they contain more computation and more information. So these are computed to detect exploit-based attacks and contains connection level content, so at the actual data within each packet of the data set, and it aggregates data with associated system level events. Some of the features here are the number of administrative operations that occur on the system during a connection, the number of failed login attempts to the connection's destination system over the connection's lifetime. And so you can maybe immediately see these kind of categories also kind of categorize the computational cost associated with generating a lot of these features and its ability to be used or pursued in real time. So what are some of the methodological challenges with these data sets, data features, and actually trying to devise a real-time anomaly-based intrusion detection system? So the first challenge here is benchmarking. As we saw with the NSL KDD dataset, a certain number of traffic features can be obtained. But if you look at some of the other public IDS datasets, these features will vary depending on the dataset used for a specific algorithm that you're looking at. So for real-time detection, which is really of interest to us right now, some of the features that could be used potentially for more accurate classification may actually require larger computational cost, or actually looking at other features at that time point to be able to use in the IDS. And so, even though there are a lot of public IDS data sets, they are relatively small compared to data sets that are given in other applications. And so, this really makes real time methodologies difficult to benchmark against a range of different attacks, right? So, we're not just interested in looking at whether a data or endpoint is an intrusion or not. What we're looking for is what type of intrusion does that data point represent, and how risky is that to the system itself? So this really makes the performance of new real-time anomaly-based intrusion detection systems difficult to analyze. So the second challenge here is computation. So if we were to use kind of standard aids, anomaly-based intrusion detection systems that use machine or deep learning methods, a lot of these work offline and require large amounts of training data for anomaly detection. Of course, when we move towards real-time domains, a lot of these methodologies are going to be really high risk and really challenging to use for real-time IDSs. And so, one of the points here is that for different attacks, it's important to understand if a smaller class of cyber features can be generally drawn or constructed for real time computation that also results in a negligible difference in accuracy. And so, a lot of these machine and deep learning methods have huge, high rates of accuracy, but they're not being done in real time. So, really, how do these algorithms work in real time, and how does the accuracy compare with the computational cost that's associated with a smaller class of important cyber features that we need to use for real time IDS? And so the optimal class of features at every time point ideally will be both computationally efficient and intrusion relevant to that specific intrusion that we're typically looking at. But will, of course, differ depending on the type of intrusion present. So the main question that we're trying to answer here at Sandia is, can a more generalizable approach be derived to tackle both computational efficiency for real-time computation and intrusion relevancy? And so reducing the feature space is really important for real-time IDS and real-time computation. Reducing the dimensionality of features is typically done through feature extraction or selection. So these aren't the same thing. So feature extraction projects the original data onto a new feature space, so it really reduces that dimension. Typical examples here include singular value decomposition, and a subset of SVD, which is principal component analysis, or PCA, which is really used widely in the literature for all types of applications. And so an important thing here is that streaming versions of these algorithms exist. And and this is more relevant to IDS or real-time IDSs. And what do I mean by streaming? I mean that the data is nowhere stored and can never be revisited unless the specific IDS actually explicitly stores them. So in the streaming sense, we have batch PCA that does principal component analysis and reduces the dimension on batches of data points, which are typically defined by the user before plugging it into the real-time IDS. And then we have streaming PCA, which actually computes streaming principal components at every time point. So on the other hand, instead of feature extraction, which reduces the dimension space, we have feature selection, and this is a different problem. This selects the most relevant features and omits irrelevant ones. For example, those features that are really highly correlated with relevant features that have already been obtained by the system. So there are a number of algorithms here. I'm just listing four, but there are quite a few. We have weight by maximum relevance, or WMR, which measures the dependence between each feature and each response. Then we have minimum redundancy and maximum relevance, or MRMR, which has been used in the literature, especially for this KDD dataset. And this uses sequential forward exploration by adding features that have maximum relevance and minimum redundancy with respect to the current feature subset. So for MRMR, in the static and the streaming cases, what happens here is that a feature set is typically divided into four disjoint sets. It's classed into irrelevant features, redundant features that could also be a part of weakly relevant features, weakly relevant but non-redundant features, and then strongly relevant features. And here, an optimal subset typically contains non-redundant and strongly relevant features. So that's something that we would like to pursue in a streaming sense. And so, especially with MR, in the streaming case, since the global information of all candidate features is unknown, and features are generally generated continuously in real time, it is very challenging to find all strongly relevant and non-redundant features from these kind of streaming features in a streaming sense with MR. And so here, the streaming task is to find an efficient and effective way to find an optimal subset from streaming features at each time point in the real-time IDS, which can be challenging given the different data types found in network traffic data, which I'll come on to, which can be like classed as continuous, categorical, or mixed type. There are then some other algorithms, including the least absolute selection and shrinkage operator, or the lasso. This is a statistical approach. This is a regularization which shrinks irrelevant feature weights to zero through regularization or penalization. Stepwise regression that iteratively constructs the regression model through the addition and preservation of features that are statistically significant. Again, this can be done in real time by performing kind of statistical p-values or hypothesis tests at each kind of real-time point. A lot of these algorithms do exist in a streaming or real-time sense that we really want to try and leverage. So with the NSL or NSL KDD dataset, we looked at the features of this dataset, and in our team, we did analyze the computational complexity of a lot of these features and its feasibility in real time, given the fact that it's broken up into basic connections, aggregated traffic features, and connection content features. So just looking at the basic connection features, a lot of these are feasible in real time just because they are given at every kind of they're given straight away at every time point. These include kind of protocol types, the packet or the connection duration, land, which is a logical indicator if your source, destination, and port numbers are equal, and the correction status or the flag. Duration is maybe not feasible in real time because we require to know exactly the duration of that connection. So we need to know exactly when that connection started, and that includes comparison of packet headers, which are incrementally updated. And so this we know when the connection ends or timeout is detected. But this does require state keeping on memory, depending on how many connections there are actually going on in the system or the network. We then looked at aggregated traffic features, and of course, these were already given to us by the KDD dataset. These included count, S error rate, and destination host count. A lot of these we don't know whether they're suitable for real-time computation, and they have kind of varying complexities in terms of computational cost. So for the count, and these are the sum of connections to the same destination IP, we do require running the activity to a specific IP address over the past 2 seconds. So feasibility in real time, we can use parallelization algorithms, but this really does depend on how big the network is itself and how many specific IP addresses we're counting in that. Then we have the S error rate. This is the percentage of connections that have activated a specific flag. Again, this requires state keeping. It incrementally updates, so this does require memory and incremental updates and counting of occurrences over the past 2 seconds. So again, depending on the network type and the size of the network, this could be feasible in real time. And then we have destination host count, which is the sum of connections to the same IP address. Again, this depends on size, whether it's feasible in real time, but it is complex. So we do need to keep the data for an unknown period of time, which is kind of challenging and high risk in real time intrusion detection systems because we don't know exactly what time period we're looking at for this particular feature. We then looked at connection content features. Again, these are the most costly because we're actually looking at the content of the packet, and we may need to look at other data sources to find more information. A lot of these features are kind of unknown in terms of their feasibility in real time, but they are high complexity. So feasibility in real time is kind of non-trivial, depending on how complex we could actually computing the features are. So we have hot here. So these are the sum of hot actions, and hot actions are like entering a system directory, creating programs, executing a program. Um, the number of num compromise, which is the sum of not found error appearances in a connection, and the sum of operations that are performed as root in a connection. And so a lot of these connection content features are highly complex in terms of we need a priori knowledge of what defines that particular feature. We do need network communication with the destination, and that might take some time, depending on how kind of quick that connection can be. And we do need to observe other features to compute it. So for the number of connections or operations performed as root, we do need to be able to compute the number of root or administrator tasks that have been initialized and used during a connection. So, using some previous studies, so a study by Iglesias in 2019, various feature selection methods were used and compared before just applying off the shelf supervised machine learning um, intrusion detection tools for attacks in the NSL KDD dataset. And just a caveat here is that the attacks or the intrusions were aggregated by just attack or no attack. So the different types of intrusions were not used in classification, just the fact that it was intrusion or not an intrusion. And given their results, they found the lasso with the KNN classifier to give the highest area under the curve under training and cross validation. And so these were some of the outputs of the lasso in terms of actually classifying a lot of their features into relevancy. And so what we see here is that a lot of the features for that are strongly relevant are basic, and a couple come from traffic aggregation. Um, and so with the basic features, a lot of them can be used in real time. And the traffic ones, we don't know how complex they are. Some of them can be used in real time, and some of them we don't know, depending on the size of the network. And again, a lot of these things will require additional computation. For example, with a count, which is the sum of connections to the same destination IP, we do need to be able to count the sum of connections, which does depend on the size of that network. With this study, they then concluded weekly relevant features. Again, some of these are basic, so we get these features immediately. We have one feature, which is the hot. These are the sum of hot actions again, which is a content feature. This is more costly to compute. And then the R error rate, which is a traffic aggregation feature. Here, a lot of these features are different. So we have categorical features, continuous features. Their complexities are different. So a lot of the basic ones are trivial, but then leading on to high complexity when we move to the content and traffic aggregation features. We then go on to negligibly relevant features, which importantly contains a lot of the content features and some of the basic features, including the duration of that connection. And again, some of the traffic aggregation features, which are typically kind of used across the board in terms of the relevancy. Importantly, like a lot of these negligibly relevant features are features that can update in real time, as opposed to the strongly relevant features, which, while they have kind of minimal computational complexity, do require further computation for real time updates. So just moving on to this feature relevancy, using feature relevancy metrics, the NSL KDD's dataset features can be classified in terms of their relevancy or importance for just across the board an intrusion or not. But as I said previously, feature importance is going to be different for different types of intrusions present. Feature types and the data sets that we're using to run our real-time IDSs. So feature importance in the studies that we've seen does not typically take into account computational cost. So, we could add a further penalization term if the computational cost is seen to be going to be high for real-time computation. And so this is going to be important for novel kind of streaming IDSs that require feature selection for intrusion detection of specific intrusions. Computational costs of new or unseen features is not easy to quantify without direct calculation. And so this is really going to be challenging for real-time IDSs that do use new data sets that we haven't tested our algorithms on before. A lot of this work is an ongoing research project that I'm leading at Sandia, where we're trying to look at how we weight computational cost in a real-time IDS, which also looks at feature relevancy at each time point for specific types of intrusion detections in a system. So just to kind of wrap up here, how do we kind of talk about real-time anomaly-based intrusion detections? Of course, some of them exist, but we've kind of seen some challenges here. And challenges with accuracy with real-time intrusion detection systems are due to changing data streams and changing or unknown computational complexities from a lot of the features that may or may not be relevant in streaming data. So feature passing in real time is challenging due to unknown computational costs, but actually devising an intelligent streaming feature selection techniques will be useful to reduce this cost, especially in real time. This feature cost analyses are really important to pursue for real-time systems if they're not being done already. And it's vital that new anomaly-based intrusion detection systems intelligently use features in a way that accurately detects new intrusions and minimizes false alarms. That is kind of typical of statistical machine learning-based algorithms for anomaly detection. Again, and I can't stress this enough, important features are attack specific. So in the example that I gave with the NSL KDD dataset, that was the features that they got from the lasso weren't attack specific. And of course, if we run a lot of these algorithms with specific attacks, we're going to get different answers. And a lot of the answers that we'll get won't be high accuracy because the data sets that we get with specific intrusions are relatively limited because attacks of specific type are kind of rare. And so, with this, supervised approaches are not going to be able to capture this information for a wide range of intrusions, giving us very high false positive rates and high false alarms. Another thing that I didn't talk about here were that attack signatures are typically modified by really kind of clever cyber criminals through, for example, encryption, fragmentation, flooding. And this gives us ever evolving data, intrusion data, and data sets. So, modified signatures, if we can detect the fact that they have been modified in some way, of course, can still benefit from traditional signature based analyses if we're able to kind of go back in the past to actually recover their signatures. While supervised methods are fast and can be applied in real time, unsupervised approaches are still going to be useful for generalizing anomaly based intrusion detection systems for various intrusion types. And so, kind of just alluding to what we're working on at Sandia, is we're working on kind of building a hybrid generalizable anomaly intrusion based system, which really leverages the advantages of knowledge based algorithms and other kind of traditional techniques with novel fast machine learning algorithms for the real time computation. Which is an important direction in the future of real time anomaly detection systems for detecting intrusions. So just a couple of references here. There are ton of references in the literature for anomaly-based intrusion detection systems, even signature-based real-time intrusion detection. These are just some of the few. Um, and with that, thank you for listening, and I'd like to hear any questions or discussions. Thank you. So there's one question here from Michelle. Are we able to receive a copy of these slides? I'm not sure. I can send these out if that's good. I can send these to Laura. I don't know if this is going to be uploaded onto the website. Maybe Laura has some questions about that. Hopefully, we can upload this onto the Women in Cybersecurity webinar website so that you can have this. So there aren't any other questions. If you have a question, please put it in the chat. I'll stay on for a couple more minutes before wrapping up.